linear functions, and linear means line. That's what you should think about right away. But this chapter we dealt with exponents, and so now we need to start working with exponential functions. And we're going to do two side by side right here so that you can see the difference between the two, because that's the best way to explain what an exponential function is. So we're going to start with this linear function, y equals 3x plus 2. And remember, a linear function always follows that y equals mx plus b pattern, where the m is the slope and the b is that starting point at the y-intercept. But all I'm going to do is just fill in this table with some easy x values, see what the y values are, and what we're going to look for is the pattern and then how that is different on the exponential function. So I'm just going to use 1, 2, 3, 4, and 5 for my x values. So when x is 1, 3 times 1 is 3 plus 2, y is 5. When x is 2, 3 times 2 is 6, plus 2 is 8, times 3, 3 times 3 is 9, plus 2 is 11, 3 times 4 is 12, plus 2 is 14, and 3 times 5 is 15, plus 2 is 17. Okay, what we want to look for here is what's the pattern. And so we're going up by 1 each time for x. So the question is, what's happening to y as we're adding 1 to x? Well, these are going up by 3. So you can see this is plus 3, plus 3, plus 3, and plus 3. And so that's how you can tell that a function is linear, is because for each value that you go up in x, you're going up in some corresponding value for y, but it's the same each time. That rate of change, up 1 for x, up 3 for y, never changes. That's a linear function. That's what it's going to look like, right? But you're adding each time. Let's compare that over to the exponential function and see how that's different. I'm going to use the same x values, 1, 2, 3, 4, and 5. But in this case, I do y equals 2 times 3, and we're going to start with x to the 1. Well, 3 to the 1 is just 3, so 2 times 3 is 6, right? So it's 6. When I do to the 2, 2 times 3 to the second power, 3 to the second power is 9, times 2 is 18, so do 18. Okay, so maybe we went up by 12. Let's see if that works to the next one. Y equals 2 times 3 to the 3. Well, that's 3 to the 3 is 27, times 2 is 54. Oh, so we did not go up by 12. You see how we didn't go up by the same amount that time. So something different is happening here. So now let's do y equals 2 times 3 to the 4th, and y equals 2 times 3 to the 5th to finish our patterns. So 3 to the 4th, 3 to the 4th is 81, times 2 is 162. And 3 to the 5th is 243, times 2 is 486. So let's just pop these in. 162, 486. All right, now let's look at our pattern. We were still just adding 1 for the x each time. But something different was happening to y, right? We were not adding, because this would be plus 12, but plus 12 would not get you from 18 to 54. So maybe it's times 3. Yep, and that works with that one. Yep, so we might times 3, times 3. So you can see here the pattern is different because we were not adding each time for the y value. Every time we went up by 1 in x, we actually multiplied our y value by 3. And you can see that in the curve. This curve goes up much more rapidly because we're multiplying those values. And so you're going to rise up much faster. And this is actually what you see if you've been looking in the news at the coronavirus testing. They talk about flattening the curve. And notice it's not a line, right? In those videos, it's never a line. It's this curve. And the reason it's a curve is because it's multiplying by some factor. They're not adding like 4 more people who get it every day. It's multiplying. And that's why you see that curve. So there's 2 ways to see an exponential function, or really 3. One is through the table, right? And you're looking for that multiplication factor. You're not adding each time to the y value, you're multiplying. 2 is in the curve. If you look and you don't see a line, you see this curve, you should think right away it's exponential. Third is in the equation itself, and the equation is always going to follow this y equals a times b to the x power. And so you're looking for that exponent, right? That x as an exponent. And so those are the 3 ways you can identify an exponential function. And now we'll talk about how we can work with them. For a function, and the steps are over here, right? The first thing we want to do is just identify, is it linear or exponential? And the way we're going to determine that is just by looking at that pattern. So if I look at my x values, I'm still adding by 1 each time, right? But what's happening to the y values as I do that? Well, I could say, well, that's plus 2, except that wouldn't work for this. So it must be times 2. And that you'll see works for each one. 8 times 2 is 16, times 2 gets me 34. So because I'm multiplying, I know that that's exponential, right? My y value is getting multiplied each time I increase my x value. Okay, so we know it's exponential, which means we know we need to use this as our basic form of our equation. So we're going to have y equals a times b to the x power, okay? So the next thing you're going to do is figure out what's your b. And the b is really simple. It's just what are you multiplying by? And you can see that that's just 2. So b is 2, right? I can just take the 2 and say that that's b. And so I could update my equation and say y equals a times 2 to the x. Okay, the last thing that you got to do is just figure out what's the a value, right? And your a value is just what's your value of your equation, what's value of y, when x is 0. It's like, what's your starting point? And I can look back at the table and I can see this. When x is 0, y is 8. So I know that my a value, right, a is 8. That's where I'm starting. That's where my x value is 0, y is 8. I'm going to just pop that in. So now I have y equals 8 times 2 to the x, and I am done. That's my rule for this equation. And you could pop in any x value you want to see what the next value is going to be. You could pop in any of those to make sure it works, and that's how you'd work with it. So now, again, linear versus exponential functions. Let's graph the function and find its domain and range. And I already included the graph. Just want to see how you would do that, and then we'll talk about the domain and range. All right, so they got a bunch of values here. We could just start with 0, right? So y, when x is 0, we'll start there. Y equals 8 times 2 to the 0. Anything to the 0 is just 1, so that's the same as saying 8 times 1, which is just 8, and that's exactly what they got. So you'd go to 0, 8, and that would be on the graph. We could just do one more, right? We could do 2 and 32. So y equals 8 times, and all I'm doing is just plugging in these x values and seeing what I get. And again, I included the table for you, but if they didn't, you would just do this. You'd pick x is 1, x is 2, x is 3, just pop them in, see what you get for y value, and then just graph those pairs, right? And if you don't have a graph paper, you can just do it on Desmos. Just type in those coordinates on Desmos and it'll show you the same thing. So anyway, to finish up this, 2 to the second power is 4, so 8 times 4 is 32. And sure enough, so we got right here, 2 and 32. So go over to 2, jump up to 32, which is right here, so 2, 32. And you can see this isn't a straight line, right? If we did that one other one, 116 was right here. And you can see a straight line is not going to connect those 3 dots, right? Any 2 dots you can connect to the straight line, but as soon as you put the third in, you can see it's not going to be a straight line. It's not linear. It's on this curve, and that curve is the sign of an exponential function. All right, domain and range. Domain is just the x values that you can use, and the range is the y values that you might end up getting based on what you can do. So the range, the domain here is you can plug in any x value you want. See, I mean, you plug in -2, -1, 0, 1, 2, 3. You could plug in 100. You could plug in anything you want. So the domain in this case, we just say it's all real numbers. And another way to write all real numbers is this R with the double bar there, okay? But it just means you can plug in any x value you want. There's no restriction on the x values. We haven't talked much about this so far. And as we move forward, we'll get into certain restrictions, x values that you can't use in certain situations. But for right now, we can plug in anything we want. And the way we say that is all real numbers. Okay, now with the range though, the range is, what are the y values that you might get? What's that range of y values that you could get? And right here, what's really important to notice is that if you look at this curve, right, we're going lower and lower on the y values as we go left, right? As we go to the right, these y values are getting bigger and bigger and bigger, and they could go up and up and up and up towards infinity, right? But as they go down, see us leveling off? That line is never going to dip below that x-axis. You're never going to get a negative y value. And the reason is if you look at the equation, right? 2 to the whatever value, 2 to the -1, it's still going to be a positive number. 2 to the -2, it's still going to be a positive number. So you're never going to get a negative value for y in here. So for the range, it's going to be all positive real numbers. And so that's basically right now all you need to think about, right? The domain is just what x values are you allowed to use, and for the most part, you can plug in anything you want. For the range, they're just looking for you to determine if there's a restriction on what you might end up with for the y value, right? Can it be negative or positive, or no, can it only be positive, which in this case is true, okay? So finally, compare the graphs. So they give you 3 graphs. You can tell they're all exponential because you see the little exponent, the x is the exponent. And they're just asking you to look at them and see how do they compare to each other. So I'm going to look at the purple and the blue one first over here. And I can see they basically have the same curve, but the purple one, every value where I'm at x, the y value is higher, right? And the reason is because for the blue line, it's just 2 to the x power. But for the purple line, I'm multiplying that by 3. So for every x value, my y value for the purple line is going to be 3 times higher because I'm multiplying it by 3. And so that they call that a vertical stretch. You're pulling it up by multiplying it by the 3. And that's all you need to say there. It's a vertical stretch of this line, of the blue line. Now, how do we compare the red and the blue lines? So you can see, actually, how do we compare the purple and the red lines, okay? So you can see the purple line and the red line kind of look the same, except that the red line is going below the x-axis and it's going down. And you can see why, because the purple and the red line pretty much look the same, except that 3 is negative. So for every x value, whatever I get in the purple line, I'm multiplying, I'm making that negative. And so if we're at 3, for the red, we're at negative 3. If we're at 6, for the red, I'm at negative 6. I'm getting the same value, but negative. And we call that a reflection in the x-axis, because you can see, if you think of this as your mirror, right? These 2 lines are reflections of each other over that line. They're symmetrical about that axis.